Okay, so welcome to section 4.8. We've talked about discrete and continuous random variables, some of their properties and examples. Then yesterday we looked at linear transformations of random variables. And I realized I made a mistake in one of my videos. I believe I said these were the rules for discrete random variables, but these rules just apply to random variables in general. And so today we'll take a look at what I mean by that statement. Now, the most important thing about random variables, and ideally what we're looking for when we combine any two data sets, is that we must assume independence. And the reason being is because we don't want the results of X to influence Y or vice versa, right? We ideally want two completely separate data sets so that we've reduced bias, we have not infiltrated any of the integrity of those distributions, so we can combine them so that our results hold valid and true. If we're working with biased data or dependent data, then these rules will not be as helpful. So always make sure to ask, is this a reasonable assumption, and are the outcomes independent of one another? Take into account really the only few dependent situations we've looked at so far are either sampling without replacement or the matched pairs experimental design. So we did this NIMSY activity already called StatLand and a few other StatsMedics activities in class. So this is just kind of an overview of the lesson here. So the rules of these combinations. So one important thing that I want you to write down here is that these rules here for the means, this is just a general rule. You can add or subtract the means, generally speaking, whether or not they are independent or not. In order to combine their spreads, though, they must be independent. We cannot just combine them if they are dependent spreads. They must be independent in order to combine the spreads. But generally speaking, we can always add and subtract the mu's here. So if I'm looking at a distribution of x plus y, well, like I said, I can just add the two means together. Or if we're looking at their difference, we can just subtract their two means. And actually, sorry, I think I'm trying to go for this color-coded scheme. One of my kiddos was like, the colors help, so as a teacher, of course, you modify so that your students can learn. So we're going to do mu x minus mu y. Okay, and then here, now in order to combine the spreads, I'm taking the spread of the first distribution, I'm taking the spread of the other distribution. When we combine the variances, we can just add the variances. So that's going to look like this, sigma squared plus sigma y squared. I can actually just add the variances together. Now, the standard deviation is where we falter. You cannot add the standard deviations. Since the standard deviation measures the distance, right, between the observations and the mean, distance here must be a positive value. And so in order to do this, since I know that standard deviation is the square root of the variance here, I'm actually going to write this as the square root of the sum of the variances. So I cannot add the standard deviations. I have to find their distance. You'll notice that this looks very similar to the Pythagorean theorem because, again, it is measuring the distance of observations and the mean. So this is, in general, addition here. Now, subtraction, we notice that the means change, but we said subtraction does not change measures of spread. This still holds true, and even though I'm subtracting these two distributions, ultimately I still am combining them. So even though it says subtraction, we're not going to subtract the variances, we are still going to add the variances because we're still combining these two data sets. If you take two smaller spreads and put them together, you're still going to have more spread. And so this idea here is that even though it's subtraction, that only changes its location. It does not necessarily look at the difference between the spreads because we're still combining the spreads. So that logic's a little weird, but just know that we never subtract these spreads here. So regardless, the only thing that's different is whether or not we're adding or subtracting the means, but combining their spreads still holds true as follows. Now, what if we are multiplying both of our distributions by a constant? And then even if we're subtracting them, this holds true. So I really should have said plus or minus here. Hopefully you can see that. I don't know if you can. And yes, I could have technically done that for these two as well, but I'll do that in my Unit 4 review later. So the plus or minus here, so ax plus or minus b, ax plus or minus by. The same holds true. You're going to multiply the constant by the means, the respective means, and you'll add or subtract those values. So mx plus b my, or mx minus b mu y. Now, same thing applies with the spreads. Well, as we learned in 4.7, in order to find the variance of the respective distributions, we're going to take the values and we're going to square them. And of course, we're not going to ever subtract them, so I'm just going to take these values here and square the constant by which I'm multiplying and add up the variances. Same logic happens for the standard deviation, regardless if we add or subtract. We cannot just add the sigmas, we have to find the distance. So in order to find the distance, we'll take the square root here. So we'll do a squared sigma x squared plus b squared sigma y squared. And again, whether b, if this is a positive or negative, it's going to be squared. So ultimately, it will turn positive. So that's how we combine our random variables here. So let's take a look at some examples, and I'm going to do 3 separate videos for this. Actually, okay, I'll tag this one on at the end here, and then we'll look at continuous combinations. So here we have the following scenario. Suppose the average SAT math score is 625 and the standard deviation of the SAT math is 90. The average SAT verbal score is 590 and the standard deviation of SAT verbal is 100. The composite SAT score is determined by adding the math and verbal portions. What is the mean and the standard deviation of the composite score here? So I have some summary statistics. I'll be able to figure these out. So I'm going to let z be equal to the composite score. And I do this because now I know that z, and you could have picked any letter, I just picked z. Composite, no, that's not a good explanation, whatever. You can pick any letter here. I just picked z, but then I realized this might be a problem when we do z-score. So for now, for this example, it's just z. So I know that z is equivalent to the composite scores here. So that's equal to the distribution of x plus the distribution of y, which means the mu of z, again, what am I looking for, would be the sum of the mu of x plus the mu of y. So what am I looking for? What does it mean? Get it, because this is the mean. Okay, sorry, lame stats joke. It's early in the morning and I'm recording in an empty classroom again. Well, I know the mean of x is 625, and I know the mean of y is 590, which would tell me that their combined average time here would be about 1,215 points, I guess, because we don't really have context. So we'll assume points. In order to find their standard deviation, again, I can't add the standard deviation. I have to find their respective variances, add those, and then take the square root first. So here, this looks like the standard deviation for x was 90, so we'll take 90 squared, plus the standard deviation of y, which was 100. So we'll square that, add those together, find their differences, and we get that the standard deviation of their combined scores is about 134.54. So that's, this is what we get, this was like an addition, right? This was a combination for adding. Now, what if I wanted the difference? So suppose we expect more students to perform better on the math portion than the verbal portion based on strategies alone. What is the mean and standard deviation of this suspected difference? Okay, so now we're going to let, we'll let W equal the difference between, well, what did we expect here? We expect better than math and verbal, which basically turns into x minus y. Okay, so The reason I'm doing x minus y here, this just comes because I expect math to be better than the verbal. So if I look at that, it's the same thing as x minus y is being greater than 0 here, or w is greater than 0, etc. And so this very simple inequality is going to come back to haunt us during inference, but it's a good way to start practicing now. So in order to find the difference here, you could also just say the difference of x minus y. Since I already defined the variable, though, I'm going to keep consistent with my notation. So the mu of w here would equal the difference of the means, which would equal the difference between 625 and 590, which gives us a difference of about 35 points. Then I look here for the sigma, and even though I'm subtracting, again, I'm combining two distributions. So I would still, since I'm combining them, I'm going to add their variances and take that square root. Well, we can skip that step because we did it above. Regardless, if we add or subtract, we're still changing the spread of the new distribution. But our distribution remains the same whether we add the random variables or whether we subtract the variables. And again, we would assume they're independent. We were not told anything about a matched pairs design. We weren't told anything about a before and after study. We were just told, here's the SAT math, here's the SAT verbal. We can assume that these are independent. It's reasonable. So this is just an example of combining some random variables here.